Hello and welcome to the tutorial on overview and importance of data quality for machine learning tasks. This tutorial will be delivered by Nitin, Gupta, Shashank, Mujumdar, Shazia, Afzal and Hima Patel. And we are all part of IBM Research India Lab. And before proceeding further with the tutorial, we would also like to thank all our colleagues at IBM Research who have helped, who are working on this area with us and who have helped put the material for the tutorial together. Okay, so this is what we are going to do as part of this tutorial. We're going to spend the first few minutes talking about the need for data quality measurement with respect to machine learning applications, and why is this very critical in today's world. And then we are going to basically do part one and part two. We are going to do a deep dive on a few data quality metrics for different modalities. So first we will talk about the structured data, and then we will talk about quality metrics in unstructured data. And finally, we will focus on the need of human in loop for data quality measurements, and what is the state of the art and what are some open challenges here. Okay, so with that, let's get started on the need for data quality for machine learning. Most of you must have seen, articles which have said that, data preparation accounts for about 80% of the time. It is the most consuming activity in a data science life cycle. The question we asked ourselves was the following, right? Why is data preparation the most challenging activity in a data science life cycle, right? And maybe we should try to understand the challenges which can help us, try optimize some of that, right? So, and that's where we started, and we said that okay, this is what a data science life cycle looks like, right? A data scientist gets data, they would do exploration, gathering, analysis, clean, build some features, build a model, right, and go and communicate the results to the user, and voila, they're done, right? But this is really a very theoretical cycle, right? In practice, a data science life cycle really looks something like the one on the right, wherein a data scientist gets the data. They would do some cleaning, build some features, build a model, and then realize the model is not working up to the expectations, so go back and do some more cleaning, build better features, build a newer model, and etc. So in reality, it is really an iterative debugging task, which is, cumbersome and time consuming. And then the question to ask is, why is this an iterative debugging task, right? Why is it not as, how we show the theoretical, picture on the left, right? And one of the reasons for that is that at the start of the process, right, even before we do anything with the data scientist or the user doesn't really know what are the challenges in the data, which is why, and then there is no straightforward way to know all of them, right? So, which is why they have to go through this iterative cycle, if you will, and discover challenges along the way, right? And it's become more of an art rather than, science, if you will. And that's precisely, which made us thinking, and which I think, drives the point towards the need for data quality measurements for machine learning or a data science life cycle. So, if we could do data quality analysis at the start of the process, so hey, here's the data, let me run this through a data quality analysis, right? It would help in the following ways, right? One, you could know the issues in the data beforehand, right? And make more informed choices for data pre-processing and model selection. It will also reduce, in some ways, turnaround time for the data science projects, because now instead of doing the iterative cycle, there is some rhyme and reason as to why one would make a particular choice for a particular data pre-processing technique or a model selection technique, right? So essentially, I mean, the goal is that data quality, if we do data quality analysis at the start of the process, it can help us to go from the right-hand side of the picture towards the left-hand side. And we may not reach exactly there, but it will help us in the process. Now let me take a concrete example. So for example, let us say in a given data set, right, we ran it through various data quality analysis and we found that there was overlap between two classes, right? So at step 0, right, at this point, a data scientist, gets the data and also gets associated information and says, okay, this is a two-class binary classification problem. And there is about 30% overlap between class A and class B. Right? This immediately gives me or a data scientist some information and says, okay, right now I do know that, which means there are some features which are weak. Maybe we need to do some better feature engineering, or I do need to pick up a model which is, complicated and, I mean, is complex and can take care of these kind of complex scenarios. Okay, so that's how that is why we think that data quality analysis is crucial for machine learning life cycles. And and that's, I think, one part of the story. And we've looked at some of these challenges, keeping the data scientist looking at the from the lens of data scientist. But really, in an enterprise data life cycle, there are several personas who work together in complex ways, and all of them are necessary to actually build to build successful models that can go into production, right? So for example, the data steward, the business user, the subject matter expert, right? And this is where we think that there is a need uh, for platforms or frameworks that allow all these different personas to work with each other in a collaborative fashion, and thus the need for human in loop techniques to so that we can build algorithms which are useful to and easy to use by any and all of these personas, right? So to put it all together, we here is what we propose that there should be a data assessment and a readiness module right as step 0 as soon as you get the data, which will analyze the quality of data, and not just analyze the quality of data, but also tell a data scientist by pointing to regions of data with low quality that here are the problems. And if a data scientist knew this at step 0, then they could make informed data pre-processing or model selection choices. Also similarly, right, I think just to reiterate the point that a subject matter, we need tools that a subject matter expert could easily use. So let's take an example here. For instance, let us say we did a data quality analysis on the data set, and we found that on the Y or the labels for the given data set, the target variable, some of the labels are noisy. And now, if a data scientist finds the label, they will need, a subject matter expert to review the noisy labels and agree before the labels can be changed, because that is principally how we have defined the machine learning problem. So there is a need for tools of how the subject matter expert and data scientist can work together, and also ease of use for the subject matter expert to say, hey, row number 5, I do agree with your recommendation that this is a noisy label and we should change it, right? So in essence, essentially, I think there's a need for algorithms that can assess training data sets, and we're going to talk through some of them today, as well as talk about some open challenges. There's also a need for all these algorithms across different modalities. So again, we're going to talk about the structured and the unstructured areas today. And there's a need to allow for complex interaction between all these personas, and that's where we need human in loop techniques to so that they can collaborate with each other very easily. And in essence, right, I think there is a strong need for automation for all of this to happen with as less manual efforts as possible, right? So moving forward, right, to summarize, essentially, we have seen that within research and even in the industry, um, lots and lots of progress has been made with machine learning models, right, to make them smarter, faster, automated, etc. Right. However, the quality of a machine learning model is going to be directly proportional to the quality of the input data. So there is a need for systematic study of measuring the quality of data with respect to machine learning tasks. And that's what we're going to focus in the tutorial today. So let's move to our first part of the tutorial, where we will be talking about the data quality metrics for structured data. Um, this is how we think is a good way to organize this section, wherein we're going to cover the following topics. We're going to cover data cleaning, class imbalance, label noise, data valuation, data homogeneity, and data transformations. Um, so let's start with the first one, right? So data cleaning, right? Maybe what data cleaning is a term that we use so often, right? So what are I think what are some things that come to your mind when you hear the word data cleaning, right? Maybe missing values, outliers, inconsistencies, duplicate rows, etc. Right? So these are some common problems, or there's some common data cleaning issues that are solved with data cleaning methods. But a more interesting question is that, do data cleaning techniques always help in building machine learning pipeline, right? And if not, right, we will talk a little bit about that, and some recent work that people have been doing in terms of building joint techniques for cleaning as well as the model. Okay. So let's start with the first one, right? Data cleaning issues can typically be divided into quantitative and qualitative issues, and there have been a lot of tutorials and which have talked extensively about integrity constraints and functional dependency constraints and so on. So this is an area that we are not going to cover as part of this tutorial, but we are going to look at issues like missing values, outliers, data linters, noise in the data, noise in the labels, etc., and pick up some of these and see how much. Let's try to ask the second question that we wanted to ask, that does data cleaning help with respect to always help with respect to building a machine learning model? And there was a very nice study which was done by, which is called the Clean ML study last year. And they precisely are asking the same question, that what is the impact of data cleaning methods on machine learning models? So this is how they have done the study, and their experimental setup is they've chosen 13 real world data sets and 5 error types, which are outliers, duplicates, inconsistencies, missing labels, and sorry, not missing labels, but mislabels or noisy labels, and missing values. And they've chosen a suite of 7 classification standard algorithms, and said and basically done the test to say that, given a particular error type, if I clean that error type, will it always impact my classification algorithm in a positive way? So that is the first question to ask, that what will be the impact of this cleaning on the machine learning algorithm? That's one. The second question to ask is that, will the cleaning technique have any negative impact on the machine learning algorithm as a result of the cleaning, right? So for example, will it induce some kind of bias in the data, right? So we'll talk about what the study found, but before we go there, this is how the study has defined what is the error type, which is missing values, and the detection method is, if an empty is entry, it can be detected as a missing value. And the repair method is, right, they have used several different types of imputation methods. Similarly, for outliers, the detection method is isolation forest or use of IQR or SD, as well as the repair methods is either delete and throw away the outliers, or impute right data in some useful fashion, right? Similarly, for duplicates, right, the detection method is key collision, and the repair method is deletion. Similarly, for inconsistency, they use the detection method which comes from a tool called OpenRefine, and the repair method is basically to merge the inconsistencies found. And we'll be talking about some of this in a lot more detail as part of the data transformation when we talk about that, right? And the final one is mislabels or noisy labels, wherein the detection method is given some ground truth, and assuming that your ground truth is, is gold standard, right? If your label is going to not agree with the ground truth, that is going to be your detection method. And the repair method, right, is going to be flip labels, right, which is quite easy for, which makes complete sense for binary classes, and for multiple classes, this is a little bit more involved, but we'll live with flipping of labels for now. Both the noisy labels part as well as detection of inconsistencies and repair of that. We will be talking about both these methods in a lot more detail in the same section. Okay, so now that we have, built our setup, that, we have a bunch of open source data sets, we have a bunch of classifiers, and we have, certain error types and how we detect these errors and how we repair these errors. What the study did is they basically, for each of these data sets, right, tried detecting and repairing these errors, and ran classification algorithms before doing any cleaning and after doing cleaning. And this is what the paper reports as the study, that of the 5 error types that they had looked at, inconsistencies, outliers, and duplicates had insignificant to slight positive impact on the data if it was cleaned. But it is also shown that for inconsistencies, if you clean it, the impact is insignificant, but it is definite that it is not going to produce any negative impact. Similarly, for outliers, the impact is insignificant to positive, but it is also possible that it could have some negative impact on the data. Similarly, for duplicates, the impact is insignificant if you clean the data out of it, but it could have negative impacts because you basically removed some points, and it could negatively impact your classifier. But what is interesting is that missing values and noisy labels came out as two error types, which clean are in general have shown to have positive impact, right, on the data set. However, for it depends on what kind of repair mechanism you use for missing values, because it could have a negative impact if the imputation is far away from the ground truth. For example, it is possible that it could induce bias in the data set, which could be the negative impact. Right? Similarly, for noisy labels, the impact is positive on the classifier if this is clean. However, if the data set accuracy originally is less than 50%, then it is very hard to say whether a label is noisy or, it generally is a hard classification problem, right? So the takeaway from this slide is that based on the general patterns that they saw across the different data sets and the different train test settings, it was found out that missing labels and missing values in general have a positive impact, and one has to be careful about what it could have a negative impact based on the repair method that is chosen. This basically, brings us to a conclusion that there, there isn't, say if somebody asks the questions, right? Data cleaning, if done blindly, may or may not necessarily improve the quality of the downstream machine learning models. The impact of it really depends on, the study found that it depends on different factors like what cleaning algorithm is used and the set of parameters used for the cleaning algorithm. It is also a little bit dependent on the machine learning model that is chosen. And there's another study and there's another paper which is called as Learn to Clean, wherein they have also shown that the order in which the cleaning operators are applied has a big impact on how much the data set is going to be cleaned. For example, one could apply missing values, one could do missing value imputation and then do outlier, or do outlier analysis and then do missing value imputation, and it could lead to different results. So, in nutshell, the conclusion out of it is that while the standard data cleaning error types and algorithms have been known, um, it is we are still there is still an open area here in terms of finding the right ones. So there is no blanket algorithm which can be used and said that, hey, once you use this will always short improve the quality, and there is the opportunity for some research work to be done in this space. Moving forward, right? So we spoke about data cleaning, and within that, we did call out the problem of label noise and data homogeneity and transformation. So this is what we will discuss in the upcoming sections. But before we go there, we will spend a little bit time on the class imbalance problem, right? And there's a reason the class imbalance problem has been very interesting, because the class imbalance problem is quite well known in the sense that it means that there's an unequal distribution of classes within a data set. And for example, let's say if you are doing fraud detection, then it is quite normal to expect that your data set uh, would have very few fraudulent cases, whereas a large number of non-fraudulent cases. Let's look at some other examples where data with one pattern is more common than other. For example, activity recognition or behavior analysis, like for example, recognition of a dangerous behavior, or healthcare problems in the healthcare space, where you are trying to analyze the severity of a cancer, or fault detection in industrial machinery, and so on, right? So there are problems that exist, and the nature of these problems is that the data will be imbalanced from a classification perspective. Now, class imbalance, right, is not a new problem. This has been known for a very long time, but and it's an important problem. However, we are going to spend a little bit time on this tutorial to talk about, what are some factors in the data that affect the class imbalance problem, and what are some open areas in this space. So let's talk about why is classification of imbalanced data hard. Typically, most classifiers, with the exception of a few, assume that the data is balanced. So if you are using some metrics like accuracy, then they are bound to show you high values, but actually your classifier might not be doing a good job, right? And that is because that there's an unequal cost of misclassification errors, where false negatives are more important than false positives. Okay, so this is where we talk a little bit about evaluation metric for imbalanced data set. And like we just said, right, the accuracy may not always be a good measure for this. And typically people have shown that F1 score and these other metrics are the ones that should be used in a scenario when you have balanced data set. But now let's talk about some more interesting parts about imbalance, right? One easy way to calculate class imbalance is to say, hey, I have a two-class problem, and I have if I count the number of points in class 1 and I count the number of points in class 2, if there is imbalance in the number of points, then I have an imbalance ratio. Thus, my problem is is imbalance, which definitely is one of the factors that affect class imbalance, but may not be. But there may be other factors that affect the imbalanced nature of the class, right? So, for example, if you look at it, right, if you look at the imbalance ratio, this is definitely a problem because the learning algorithm is going to be more biased towards a majority class, and it's possible that in some cases, minority sample can be considered as noise, or in the confusion region, priorities can be given to the majority classes. However, the question is that is imbalance ratio the only cause of performance degradation in learning from imbalanced data? No, right? So let's look at a few other factors that will affect uh, that will affect the class imbalance problem. The first one is presence of overlap in the data among the majority and the minority class, right? So in this case, it is possible that the minority data points can be just considered as noise because it's a small number of points from the minority class in the overlapping region, right? So beyond counting on the number of points, how the data is distributed between the majority and minority classes play a role, and class overlap between the majority and minority classes is definitely a factor that affects imbalance. The other thing that affects imbalance is that if your minority class is fragmented into smaller sub-concepts, right? So we are anyways in the scenario that the minority class has much lesser points than the majority class. But now assume a scenario that the number of points within the minority class, they are still divided into smaller sub-concepts or clusters, if you will. This affects the problem of class imbalance even more. And this is a very and one could expect a problem like this to occur because let's take the example of fault detection in industrial settings. The fault detection methods could be, and there could be different reasons by which a fault occurs in a industrial machinery. Hence, it is quite possible that within the minority class, one could see concepts forming up where each concept relates to the kind of fault from the machinery. Similarly, data set size, right? So the data set size is another factor that affects the imbalance. So having a data set of size 100 versus a data set of size 10,000 is going to have a difference. Right? And frankly, the point is that all these effects in a combined way affect the imbalance ratio much more than just counting the number of points. Right. So what we can see here is analysis that was done by authors of the paper Overlap versus Imbalance, where they have where they have done several experiments to show how with the variation of overlap and variation of imbalance and variation of both, how do the F1 scores change across the different settings? Okay, and we could see that for almost all cases, the if you vary both the F1 score, we can see that there is a trend that the scores that all of these curves decrease as you move from left to right, and as you are increasing the issue in this case, let be it overlap or be it imbalance or be it a combination of both, right? So the red line shows that as you increase, for example, in this case, as you increase the number of issue points which have overlap and imbalance, the score is going to reduce, right? And each of this different plot basically signifies the same experiment for different data sizes, and we can see that data size also has an impact on the same. So what should be done, right? So what we have seen so far is we have seen cases wherein class imbalance is an important problem. class imbalance, the most easy way to find out if there's a class imbalance or not is by counting the points in the majority class versus the minority class. And we have also seen that between the majority class and the minority class, based on how the data is distributed between the two classes, other factors like overlap or presence of small subconcepts can further aggravate the problem of class imbalance. And typically in literature, people have shared various mechanisms of dealing with modeling strategies for imbalanced domains. As part of this tutorial, right, we will talk about the resampling kind of methods in the data space of what can be done, right? Since we are going to look at everything from the view of data quality analysis. So resampling methods, there are three standard and very well-known type of methods. Either you can oversample the data, you can undersample the data, or there are ensemble-based techniques where a combination of oversampling and undersampling techniques are used. However, the bigger question to ask is that, across does resampling, right? So any of the other types, any of the above types, be it oversampling or be it undersampling or be it an ensemble method, will it always help with respect to classification, or can we say that is the impact of imbalance recovery method same on all the data sets? And the answer to it is no, right? And which is why so let's look at this example which has been referenced in the paper Bayes Imbalanced Impact Index. And the authors basically bring out three cases here, where case one, the majority and minority class samples are very well separated with each other. And in this case, right, if they're very well separated, there's a very high probability that one could still build a good classifier that could separate the two classes here. Let's look at the scenario B, wherein there is a complete overlap between the majority and minority class, and in those scenarios, doing undersampling or oversampling, etc., may have very little to no impact on the prediction accuracies of in the prediction metrics, be it F1 or another metric of choice for the minority class. The third kind of case is partially overlap, where some samples of the majority class are going to overlap with the minority class. And in this scenario, it is shown that based on if we choose the right method, it is possible that it could have an impact. However, right, however, in this scenarios also, one has to find out the right set of right repair mechanism, or the right set of oversampling, undersampling, or a combination to see a high impact. So to conclude this section, right, we would say that class imbalance is definitely an important problem. The data distribution factors affect the class imbalance problem beyond just the difference in the number of points in the two class. And even with the plethora of techniques available for oversampling or undersampling of data, based on how the data distribution is, they will have a different impact on the classifier accuracy, right? And hence, to conclude, this is still an open problem as to determination of whether one should resample or not. Given a class imbalance problem is an open problem, and there is scope for research in this space. We will now move on to the other parts of the data quality metrics for structured data. And I would invite my colleague Nitin Gupta to take us through the rest of the presentation.